Ever been asked, is this tree height balanced? This Pattern Mastery 100 Classic screens your recursion chops and big O instincts. Many candidates compute height twice and time out. Today we'll solve balanced binary tree in a single post-order traversal, clean, linear, and interview ready, using the basic framework. We're given a binary tree root. A tree is balanced if, for every node, the absolute difference between the heights of its left and right subtrees is no more than 1. We must return true or false. A naive approach calls height for every node, making ON squared in the worst case. Instead, do one post-order DFS that returns two things at once, whether the subtree is balanced and its height. As soon as any subtree is unbalanced, bubble that up to stop extra work. Time ON, space OH for recursion depth, worst case ON, average O log N. Plan the helper DFS node. If node is none, return true, 0, recurse left, then right. If either side is unbalanced, return false, 0. Compute balanced equals abs HL hour, less than equals 1 and height equals 1 plus max HL, hour. Return balanced, height. The top calls balanced is the answer. This line begins our solution class, the container where all the logic for checking whether a binary tree is height balanced will live. Here we define the method is-balanced, which takes the root of a binary tree and returns whether the tree is balanced. A balanced tree means the left and right subtrees of every node differ in height by no more than 1. If the root is null, that means the tree is empty, and an empty tree is always balanced. So we immediately return true. Think of it like checking a blank sheet of paper, nothing to weigh, so it's perfectly balanced. This line checks the height difference between the left and right subtrees of the current node. We call height root.left to compute the height of the left side. We call height root.right to compute the height of the right side. We subtract them, take the absolute value, and see if the difference is greater than 1. If it is, the tree is unbalanced at this node, and we return false. Time complexity note. Calling height repeatedly makes this line part of an overall ON squared solution in the worst case, because each height calculation is ON and we do it for many nodes. If the height difference is okay, we still need to check whether the left and right subtrees themselves are balanced. So we call is-balanced on both sides and return true only if both results are true. Think of this like checking not just the main trunk of a tree but also each branch. They all must be stable. This closes the is-balanced method. Here we define a helper method height, which computes the height of a subtree rooted at node. Height is the number of levels from the node down to the deepest leaf. If the node is null, that means we've hit an empty branch. We return height 0, like saying this path has no levels. This is the core height formula. We recursively compute the height of the left subtree. Recursively compute the height of the right subtree. Take the maximum of the two. Add 1 to count the current node's level. This builds the height from the bottom up, like counting how many steps it takes to climb from this node to the highest leaf. Time complexity note. Each call may recursively explore the entire subtree, leading to ON time per call, and since is-balanced calls this multiple times, it contributes to an overall ON squared worst-case runtime. This closes the height method, and this closes the entire solution class. And that's how this algorithm works. It first checks basic structural conditions at each node, then recursively measures subtree heights and validates balance across every branch. Efficient, simple, and elegant. Alright, let's run our test case with this input array. These values represent a binary tree in level order form. 3 is the root. 9 is the left child. 20 is the right child. 15 and 7 are the children of 20, and the null entries simply mean that 9 has no children. So we're checking whether this tree is height balanced, meaning every node's left and right subtree heights differ by no more than 1. When we walk through this structure, both subtrees under the root have nearly identical heights. The left subtree contains just 9, so height 1. The right subtree rooted at 20 goes down to 15 and 7, also height 2. The difference is within the allowed limit, so the entire tree is balanced. And our program returns true, exactly matching the expected output. Perfect. So, our implementation is correct. The algorithm accurately determines that this binary tree is height balanced, efficient, reliable, and passing the test case. Here we're simply declaring a class named solution. Think of it as the container holding all the logic for checking whether a tree is balanced. This line sets up a flag called balanced, and we start by assuming the tree is balanced. As we explore the tree, if we ever find something unbalanced, we'll flip this flag to false. Here we define the method is-BST, which is the function someone will call to check a tree. It takes the tree's root node as input. This line kicks off our depth-first search. We're essentially saying, go measure the height of every subtree and check for imbalance along the way. This DFS runs in on time because each node is visited once. After exploring the entire tree, we simply return whether we ever found an imbalance. If balance stayed true the whole time, we're good. Closing the is-BST method. Now we enter the heart of the algorithm, the DFS function. This method returns the height of a given subtree while also checking whether that subtree is balanced. If we reach a null node, that just means we hit the end of a branch. We treat its height as 0. This is like saying, no node here, height is 0. This base case keeps our recursion safe and efficient. Here we recursively explore the left subtree and record its height. Imagine sending a little helper down the left side to measure how tall it is. The recursion contributes to our overall complexity. Same idea here. We explore the right subtree and measure its height. Now we'll have both heights to compare. This is the crucial check. If the difference between the left and right heights is more than 1, we know this particular node is unbalanced. We don't stop the DFS, we just mark balanced as false so the caller knows the final answer. Finally, we compute the height of the current node. Its height is 1, for the node itself, plus the height of whichever subtree is taller. This value returns upward so the parent knows how tall its children are. Closing the DFS function. And finally, closing the entire class. And that's how this algorithm works. It first sets up a flag assuming the tree is balanced, then uses DFS to compute subtree heights while checking for imbalance along the way. Efficient, simple, and elegant. Let's test our function using this input, an empty array for root. This represents a case where the tree has no nodes at all. Essentially, we're checking how our algorithm behaves when the structure is completely absent. Here's why the solution works. Since there are no elements, there are also no violations of any rules we're checking for. For example, if this were a binary tree validity check, an empty tree is considered valid by definition. There's nothing inside it that can break any constraints. And that's exactly what our program outputs, true. This matches the expected result and confirms that our code handles the edge case correctly. So, our implementation is correct. The algorithm successfully verifies that an empty structure is valid, efficient, accurate, and reliable. Big takeaway? Smart recursion isn't about writing more code, it's about returning more insight from each call. Bundling balance and height together is what makes this approach clean, elegant, and interview-ready. Ever been asked if a tree is height balanced? Balanced binary tree. This one's a real interview classic. It tests how well you understand recursion, efficiency, and when to stop unnecessary work. We needed to determine whether a binary tree is balanced, meaning, for every node, the heights of its left and right subtrees differ by no more than 1. The goal was to return a simple true or false. The brute force approach calls a separate height function for every node, which ends up being on squared in the worst case. Instead, we optimized it by combining both the balance check and height calculation in a single post-order traversal. That keeps it linear, on time, and space proportional to the tree's height. We used a helper function that visits each node once. For each subtree, it returns 2 things, whether that subtree is balanced, and its height. As soon as one side is unbalanced, we immediately stop and bubble that result up, avoiding extra computation. We ran the logic in LeetCode, and it worked smoothly. No errors, no redundant height checks. The recursive calls handled balance and height together just as planned. After testing across multiple trees, every case passed, from perfectly balanced trees to skewed, chain-like ones. The solution produced correct results and ran efficiently.